So good morning everyone. Yesterday we discussed about the different type of electrical faults and the abnormal operating conditions. Now today we will first start with the what we have discussed, the stator faults. That is, we will discuss the stator faults, and as you know the fact that the three-phase armature winding on the stator can develop the phase as well as the ground faults, and another possibility of it is the interturn fault on the same phase. So in case of stator, we will have the phase fault, we will have the ground fault, and we will have the interturn fault on the same phase. Now we will start with the stator phase and the ground faults. So stator phase and the ground faults. Phase and ground faults on the stator can be detected by the percentage differential protection as shown here. So it can be detected by the percentage differential protection, and this type of scheme is also known as longitudinal differential scheme. So this type of scheme is known as longitudinal differential scheme. So this type of scheme is known as the longitudinal differential scheme to differentiate it from the another differential scheme which is known as the transverse differential scheme that we can discuss. This transverse differential scheme, it is used to detect the interturn fault. So this is known as the longitudinal differential scheme, and for the interturn faults, we are using the transverse differential scheme. Now, as you have studied in detail about this differential protection, and in this case, since as you know the fact that there is a difference between we have discussed the differential protection of the transformer previously, and as you know the fact that the difference between the differential protection and the power transformer is this, that you can say that these are actually the voltage difference between, in case of transformer is there, then another things would be there, tap changer would be there present in that. So the percentage bias setting of the this generator differential relay is quite small compared to the power transformer. So one thing you have to take into consideration, that the percentage bias of the generator differential relay, percentage bias of generator differential relay, percentage bias of the generator differential relay is small compared to the power transformer, is small compared to power transformer. Now what we do, we can have a small table, we can make a small table so that you can get an overview of different things which are happening, in this case power transformer and the generator. Now let us suppose that we have the power transformer here. We can write the power transformer and we can write the generator here. Now in this case, primary and secondary voltages are different. In case of transformer, the primary voltage and the secondary voltage are different. And in case of a generator, same voltage for CTs on two sides of the generator. Same voltage of CTs on two sides. Now second one, turns ratio are different because of the ratio of transformation of the transformer. Turns ratio are different due to the ratio of the transformation, and in this case you will see the turns ratio of the CTs on the two sides are same. Turns ratio of the CTs on two sides of CTs on two sides, they are same. Now third one, tap changer may be present. Tap changer may be present and no tap changer is there. So actually now what happens that this gives rise to a large spill current during the normal load and external fault in case of the transformer differential protection than in case of generator and this differential protection, because these things are there in case of power transformer and generator, and large spill current during the normal and external fault would be there in that very case. Now normally the percentage bias setting, if you see the percentage bias setting of generator is nearly about 5 to 10%. It is of generator is 5 to 10%, and this percentage bias is adequate for longitudinal differential protection of generator stator winding, whereas in case of the transformer, if you see in case of transformer the percentage bias setting of 20 to 40% may be required. 20 to 40% may be required. We have discussed in transformer part also. Now the longitudinal differential scheme caters for phase as well as the ground faults. So whatever we have discussed, that the phase as well as the ground faults, it is these two are actually catered by the longitudinal differential protection. So it is catered by, these two are catered by longitudinal differential protection. So phase fault and the ground faults, and it is unable to detect the interturn faults between the turns of the two phase. So that it can do, but it cannot detect the interturn fault. Now we will discuss the interturn fault. Now the protection that is used for the interturn fault is the transverse differential protection. The protection that is used is the transverse differential protection. It is transverse differential protection. The protection scheme that is used is the transverse differential protection. And now what happens that to apply this type of protection, a special type of split winding is required, as shown here. A special type of split winding is required for that particular protection, transverse differential protection, which is used for the interturn faults. And the current in each parallel section is now compared with the other section. Like you have the current is 3000 ampere in this and 3500 ampere in this. So the current in this each parallel section is compared with that in the other section. And if there is any interturn fault in one section, then you can say that the current will differ and flow as spill current through the overcurrent relay. As shown here, we will have the current of 3000 ampere and the current of 35500 ampere. Now because of interturn fault, it is reduced. In that very case, the current is reduced. Now when the current is reduced, these are interturn fault, that is, it may be shorted. So here we will have the current of 3000 ampere, here we have the current of 3500 ampere, and as a result the remaining current will flow through this overcurrent relay. Now again I can say that the half of the winding in which there is the interturn fault is carrying nearly about this 3000 ampere, and A healthy half actually carries the 3500 ampere, and the current entering the phase C winding as a whole is 6500 ampere. From here it is 6500 ampere, which is same as that it is leaving. That is, this current is 6500 ampere and which is leaving is 6500 ampere. Therefore, a longitudinal differential relay would be incapable to detect the current, because you will see that whatever the current is entering here in this phase is 6500 ampere, and here also it is 6500. And if suppose we are using the differential protection here in these two parts, then you will see that no spill current is there, and as a result the longitudinal differential protection will not work in that very case. So longitudinal differential protection will not work. It will not work, and because of the splitting of the winding and transfer connection of the CTs, there is a spill current. If you see, there is a spill current of 0.72 ampere. If you see that this is 4.28 ampere and this is you have 5 ampere. So spill current of 0.72 ampere in the transverse differential relay is there, and a setting of, say, you can have a setting of nearly about 0.5 ampere. It will be enough to detect the fault, because the current which is flowing through it is 0.72 ampere. So this is how we have discussed or catered this type of fault also, that is the interturn fault. And the interturn fault, it can be detected by this interturn fault, it is detected by the this transverse differential protection. Transverse differential protection. Now let's come to rotor faults. It is about this fault, and let's come to the rotor fault. Rotor faults. Now, as you know the fact that the rotor carries the field winding which is kept isolated from the ground. Rotor carries the field winding which is kept isolated from the ground, as you have seen. Now, neither the positive nor the negative terminal of the DC supply is grounded, as you have seen here. So, any ground fault on the rotor winding, this is the ground fault in the rotor winding, does not affect the working of an alternator. However, a subsequent fault would cause a section of the rotor winding to be short-circuited, giving rise to secondary flux which opposes the main flux in the proximity of the shorted turns, causing the distortion in the distribution of the main flux. Now what happens? That if you see the ground fault in the rotor does not affect the working of the alternator. However, the fault would cause a section of the rotor. It would cause a section of rotor. It would cause a section of the rotor winding to be short-circuited. And giving rise to secondary flux which opposes it, giving rise to the secondary flux which opposes the main flux, main flux in the proximity of the shorted turns, and as a result it causes the distortion of the main flux. So the main flux is getting distorted. It causes the distortion of the main flux, and the flux will get concentrated on one pole, but It will not get concentrated on one pole and dispersed over the other and the intervening surfaces, and the resulting asymmetry in the electromagnetic forces will cause the severe vibrations in the rotor. So this distortion, this will get concentrated in one pole and dispersed over the other and intervening surfaces, and the asymmetry in the, because of this distorted flux, there is the asymmetry in the electromagnetic forces. Asymmetry in electromagnetic forces there is the asymmetry in the electromagnetic forces, and which will cause the severe vibration, results in the vibration. It results in the vibrations of the rotor. Now, in the modern turbo alternator, the inertia of the rotation is very large and the rotor to stator clearances are very small. So, there is the likelihood of the permanent damage to the turbo alternators. So, because of the vibration in the modern turbo alternators, if you see that this inertia is large, that is, the inertia is large and the clearance is small, that is small air gap. Our air gap is small, so it will cause the permanent damage to the turbo alternator. So as a result, the turbo alternator can be permanently damaged. It can be permanently damaged. So instances has been reported where during the rotor faults, because of the severe mechanical stresses, structural damages are caused. So from this we will see that the very first fault on the field winding must be detected and the set tripped in a controlled manner. Now the figure shows an arrangement for the rotor earth fault detection and the protection as shown here. Now wherein in this case you will see an external voltage source is superimposed. We will have this voltage source, and this voltage source is actually superimposed on the rotor circuit, and the external voltage source is grounded, so that very first rotor earth fault causes a DC fault current to flow, which is easily detected by the overcurrent relay. So this is how it can be done. So what is there? We have the external, in this case you will see that we have the external voltage source, which is this external voltage source. This is actually superimposed on the rotor circuit. This is superimposed on this rotor circuit, and the external voltage source is grounded, so that the very first rotor earth fault, you can see this is grounded, and so that the very first rotor earth fault, it will trip the relay. So whenever the fault is there, so this part is also grounded, so the current would flow through it, and as a result it will trip the overcurrent relay. So this is about the rotor faults. Now we will discuss the abnormal operating conditions. Now we will discuss the abnormal operating conditions, and under the abnormal operating condition we will first discuss the three-phase stator winding in case of electrical and unbalanced loading. Now what are abnormal operating conditions? As you know the fact that a generator cannot be considered as an isolation because of very large number of other equipments which are connected to it. Even there is no electrical fault in the generator, if one of the associated equipment or auxiliaries develops a fault, then it has serious implications for the generator. Even auxiliary equipment connected to the generator is likely the source of this trouble. So there are a large number of possible faults as well as combination of the faults on these equipments that threaten the operation of the particular generator. So there were instances when there is no direct electrical fault in the generator, but one or more of its associated equipment developed a fault, or an abnormality and may lead to an abnormal operating conditions which may or may not be serious. So all the abnormal operating conditions need to be detected as quickly and sensitively as possible so that the corrective action can be taken and a possible shutdown is avoided or anticipated. So we must have the anticipation of that. So in this we will discuss the unbalanced loading. First we start with the unbalanced loading, that is which is under the this three-phase stator winding. So what is unbalanced loading? Now let us discuss this unbalanced loading with this flow chart. If you see, if there is an unbalanced loading is in a generator, that is generator is running at the steady state. Now if there is unbalanced loading in the generator, then the stator currents have the negative sequence component that you already know. Whenever there is the unbalanced loading is there, then in that very case, the negative sequence component is there in the stator, and the stator field due to this negative sequence component, because negative sequence components rotates in the opposite direction. So it rotates at the synchronous speed, but in the direction opposite to the direction of the field structure on the rotor. So the stator armature MMF due to the negative sequence rotates at minus ns RPM. So the negative sequence stator armature MMF rotates at minus ns, while the rotor field rotates at plus ns, as you have seen. The field winding is rotating at plus ns. So therefore there is the relative velocity between the rotor and the field due to the negative sequence currents of 2 times ns, as you have seen here. Now this causes a double frequency currents, that is 2 nsp divided by 120, which is induced in the rotor core and the winding. So this double frequency current of large amplitude is induced in the rotor conductors and the iron, and heat is generated. So as you know the fact that how the heat is generated, whenever we have as you know the fact that the eddy current loss or the iron loss of the rotor, as you know the fact that the eddy current loss or the iron loss of the rotor, iron loss, eddy current component of the iron loss, that is eddy current component of the iron loss, so it is proportional to F square maximum flux density square, while the hysteresis loss is proportional to F B max n, where the value of the n is 1.622, which depends upon the core material. Now, both the eddy current as well as hysteresis loss increase due to the double frequency induced currents in the rotor. So both these will increase due to the double frequency currents. Now, if you see, if the stator carries the unbalanced current, then it is the rotor which is overheated. Now, how long the generator can be allowed to run under the unbalanced loading depends upon the thermal withstand capacity of the machine. It depends on the thermal withstand capacity of the machine, which in turn depends upon the type of cooling which is adopted, which of course depends upon the type of cooling which is adopted. Now, the rate of heat generation is proportional to I square R, while the heat energy is proportional to I square R into T, and T is the time. And let us suppose that we are considering as I2, and I2 is the negative sequence current. So let I2 is the negative sequence current. Since the capacity of particular machine to safely dissipate energy is limited to a certain value k, then you can say we can write I2 square RT equals to k, and let us assume in this case the R to be constant and let it be small k, R to be constant, and let us suppose that k equals to k by R. Now we get the thermal characteristics of the machine as I square T equals to k. These are the thermal characteristics of the machine, and in other words, the time t for which the current I2 can be allowed to flow through should be less than or equals to, it should be less than or equals to, that is t should be less than or equals to k divided by I2 square. Now this is actually the current time characteristics. So this is known as the current time characteristics. Now, as you know that this characteristics is similar to the extremely inverse type overcurrent relay. So this characteristics is similar to extremely inverse type overcurrent relay. So this is extremely inverse type overcurrent relay, and there's an inverse type overcurrent relay which is fed with the negative sequence component of the stator current, gives the protection against the unbalanced loading of the generator. That is, if we have this overcurrent relay, if we have the overcurrent, what we do in this protection, what we do, we take this stator currents, we find out the negative sequence, we use the negative sequence filter in that, and since the characteristics of this relay is the extremely inverse type overcurrent relay, so an inverse type overcurrent relay which is fed with this negative sequence component, it will definitely gives protection against the unbalanced loading of the generator. Now so this is the logic which is used for that what we do, we take the stator current, then we will have the negative sequence component, and then because of the unloading of that, and then that negative sequence current, this overcurrent relay with the inverse characteristics, it can be used to detect that, and then definitely we will have the trip circuit breaker of the generator. So this is how this protection is done. Now next we will discuss with the overspeeding. Now, as you know the fact that the turbo, let us suppose we have the turbo alternator which is supplying the rated electrical power to the grid. So let us suppose that PE is the rated electrical power which is supplied to the grid, and then we will have the mechanical power. PM is actually the mechanical power. Let us suppose that PM is the mechanical power and this electrical power is supplying to the grid. Now let us suppose we have neglected the losses and machine runs at the constant speed of synchronous speed, that is NS. Now consider that due to some fault the generator is tripped and disconnected from the grid. Let us suppose that the generator is tripped and disconnected from the grid. Now it is disconnected from the grid, and in that very case previously what was there, PM equals to PE. Now we will have no it is disconnected from the grid, so mechanical power cannot be suddenly reduced to zero. So we'll end up in a situation where the generator has a full input mechanical power but no output electrical power. And this would, what it do? It will accelerate and to a very dangerously very high speeds, and if the mechanical input is not quickly reduced by the speed governing mechanism. Now, the protection against such an eventuality, it can be provided by sensing the overspeeding and taking steps such as operating the steam valve so as to stop the steam input to the turbine. Or you can say the speed governing mechanism or the speed governor of the turbine is basically responsible for detecting this condition that you have already know about that, being a student of power system. So the overspeeding can be detected by an over frequency relay or by monitoring the output of the tacho generator mounted on the generator shaft. So what we do, we have the tacho generator which is mounted on the shaft, so it will detect the speed, or it can also be detected by the over frequency relay which is used for that very purpose. So the logic is that it will detect the overspeed. Yes, if the speed is high, then it will stop the steam supply to the turbine, and it starts the shutdown of the generator. So this logic against the overspeeding, it is shown here. How we can do that? We can use the over frequency relay in that very case, or we can monitor the output by the tacho generator which is mounted on the generator shaft. Now we'll discuss the loss of the excitation, another abnormal condition, that is the loss of excitation. As I already know that big generators have the excitation on the rotor. So what are the main causes of the loss of the excitation? So certain causes would be there, that loss of field to main exciter, loss of field to main exciter, then accidental tripping of field breaker, accidental tripping of field breaker, then after that we will have short circuit in the field winding, then we will have port brush contact in the exciter, then we will have field circuit breaker latch failure, field circuit breaker latch failure, and loss of AC supply to the excitation system. Then loss of AC supply, because that AC we are converting into AC. AC to excitation, loss of AC to the excitation system. Now as you know that the generator develops both the real as well as the reactive power as shown here. It will deliver both real and the reactive power to the grid. The real power comes from the turbine, while the reactive power is due to the field excitation. So as you know the fact that this real power, it comes from the turbine, the reactive power come from the field excitation. It comes from the field excitation. And consider a generator delivering the complex power to the grid, that is PE plus J QE. Now corresponding to the real power, there is a shaft mechanical power input PM, and corresponding to the real power PE, there is the shaft mechanical power PM, and corresponding to reactive power QE, we will have the field current, that is IF. Now consider that the field excitation is lost. Now let us suppose what happens, that field excitation is lost while the mechanical input remains intact. Since the generator is already synchronized to the grid, it would make an attempt to synchronize with the grid. So it will make an attempt to synchronize with the grid, and by running as an induction generator. So it will run as an induction generator. Now under the induction generator, what it do, the machine speeds up slightly above the synchronous speed, that is ns, and draws the excitation from the grid, that is draws the reactive power which is required from the grid. Operation as an induction generator necessitates a flow of slip frequency current in the rotor and the current flowing in the damper winding and also in the slot wedges and the surface of the solid rotor body. So operation as an induction generator, it necessitates the flow of slip frequency, current in the rotor, then current through the damper windings, and slot wedges and surface of the solid rotor body. Now there are two possibilities arises out of that. Now what are these two possibilities which arises out of that? We can discuss that. So we will have it starts running as an induction generator, and there are two possibilities. Either this grid, it will be able to meet the requirement, reactive power requirement, fully or partially, and if the grid is able to fully satisfy this demand for reactive power, the machine continues to deliver the active power PE but draws the reactive power, that is, let us suppose QLOE MVA, and there is no risk to the instability of the system. However, as you know the fact that the generator is not designed as an induction machine, so the abnormal heating of the rotor and overloading of the stator winding will take place. So abnormal heating of rotor and overloading of the stator takes place. Now, if the grid will be able to meet the reactive power demand only partially, then fully. We will discussing about if it provides fully. However, if the grid will able to meet the reactive power demand only partially, then in that very case, it would be reflected by a fall in the generator terminal voltage. So there is the fall in the generator terminal voltage, and generator would be under excited, and there are certain limits at the degree to which the generator can be operated within the under excited mode. So generator will be under excited. However, there is the limit to which it can be under excited, or it can operate in an under excited mode, and therefore operation in case of loss of excitation must be quickly detected and checked to avoid any shutdown of the generator. Now the simplest method by which the loss of excitation can be detected is to monitor the field current. Now the simplest method by which the loss of excitation can be detected by by monitoring the field current. By monitoring the field current. Of the generator, and if the field current falls below the threshold, if the field current is below the threshold, the loss of field signal can be raised. The loss of field signal can be raised, and the complicating factor in this protection is the slip frequency current induced in the event of the excitation and running as an induction generator. So that is the complicating factor, that is the slip frequency current induced. That is the complicated factor. Now, second thing, the quantity which changes most when the generator loses the field is the impedance. Now, quantity which changes the most when the generator loses the field excitation is the impedance. Let us suppose Z is the impedance measured at the stator terminals. So this impedance is measured at stator terminals. On the loss of the excitation, the terminal voltage begins to decrease. When the excitation would be lost, then the terminal voltage will begin to increase, and as a result, current begins to increase. There is an increase in current, and the resulting in the, because we have Z equals to V by I, so this started decreasing and this started increasing. So what will happen? It results in the decrease of the Z. So result in the decrease of the impedance and also change in the power factor. So there is also a change in the power factor. So loss of excitation, it can be detected by the Moore relay located at the generator terminals. As you have seen that we have the Moore relay which is located at the generator terminal, which is used for that very purpose. So we call it as the offset Moore relay. For protection against the loss of excitation. Now, as you during the normal steady state operation, the impedance seen by the stator terminals, that is the apparent impedance, it lies in the quadrant first. It lies in the quadrant first of the RX plane. More later we have explained in the distance protection also, as shown here. So during the steady state operation, the impedance seen from the stator terminals, that is the apparent impedance, it lies in the first quadrant. Now when the excitation is lost, now in that very case the apparent impedance enters this quadrant number 4th. The exact locus of the apparent impedance, the rate at which it is traced, depends upon the initial complex power that was being delivered by the generator. And now if the initial complex power was high, then the locus is traced out quickly like this here to the trip region. And if the initial power output was low, then the locus is traced out rather slowly. It will take some seconds. Now, in order to keep the generator online as long as it is safe, the generator may not be instantaneously tripped in case of loss of excitation, because we have to take into consideration all these facts, because loading is there and everything is there. Now, as soon as the loss of excitation is detected by the relay, an alarm may be sounded and an attempt may be made to see if the excitation can be restored or not. Now, the Moore type relay with an offset characteristics may be used for the protection against the loss of excitation. The offset is by an amount of this xt by 2. This is the delay. This is the delay by an amount of, this is offset, to take into consideration loading and all these factors, and it is by an amount of xt by 2, and the impedance setting of the relay is xd. The impedance setting of the relay is xd at an angle of minus 90 degree. At an angle of minus 90 degree in this. So, in order to give the time for the changeover to the standby exciter by the control circuitry, the relay operation can be delayed by about 0.5 to 3 seconds. So this is how the offset Moho relay, which is the distance relay, which is used for the detecting the loss of excitation. Now the another abnormality is the loss of prime mover. Now in case of the loss of prime mover, that is prime mover means that loss of the mechanical input. So the mechanical input in that very case is 0. So the machine continues to remain synchronized with the grid. Now it will remain synchronized with the grid, however running as a synchronous motor, because what it do, it will take the active power from the grid. The machine now draws a small amount of active power compared to its rating from the grid in order to drive the turbine and meet the losses which are taking place in the machine, and at the same time the machine supplies the reactive power to the grid since its excitation is intact. So what it do, it will take the active power from the grid and it will give the reactive power to the grid. So running in this mode is not harmful to the generator, but it is definitely harmful to the prime mover like steam turbine. So definitely it is the harmful to the steam turbine. Which is the prime mover. And normally if you see that the loss of steam supply to the turbine, it causes the loss of prime mover, and that is when the steam supply is lost, loss of steam supply, so as a result it causes the loss of prime mover. And when the machine runs as a motor, there is the churning of trapped steam in the turbine, causing the objectionable temperature rise and damage to the blades, and loss of prime mover needs quick detection followed by the tripping of the generator. So the machine, when the machine runs as a motor, as you see, there is the churning of trapped steam in the turbine. There is the churning of trapped steam. There is the churning of so there is whenever it runs as a motor, there is the churning of trapped steam, and along with that causing the objectionable temperature rise and damage to the plates, and therefore the loss of prime mover needs quick detection followed by the tripping of the generator. So when the prime mover is lost, the generator starts drawing real power from the grid, supplying the reactive power to the grid. The real power drawn from the grid is quite small compared with the generator rating, and the generator draws the real power which is just enough to meet the losses and the load put on it by the turbine. As the magnitude of the stator current is smaller than when it was generating. Hence, if you see from this, the magnitude of stator current is smaller because it is taking a very small amount of the active power. So the magnitude of the stator current is smaller than when it was generating. However, it goes a shift of 180 degree. It goes the phase shift of 180 degree. Now, from this what we conclude that if we use the directional relay with the maximum torque angle of 180 degree using the phase angle conventions, then it would detect the loss of prime mover as the current phasor would reverse and enter the trip region. However, the magnitude of this reverse current phasor is quite small compared to the forward current, as the generator draws just enough real power to meet the losses and drive the turbine. Hence, the directional relay for detecting the loss of prime mover needs to have a high degree of sensitivity compared to the directional relay used for the overcurrent protection. The scheme which is used, that we can use the directional relay with an MTA of 180 degree using the generator phase angle conventions, and it would detect the loss of prime mover as the current phasor would reverse, as you have seen that here it was the current phasor. Now the current phasor is reversed and it moves to the trip region in that very case. And one more thing we have to take into consideration, since the magnitude of the reverse current phasor is quite small, because it is taking a very less amount of, it is small because it is taking a very less amount of the active power, that is real power, which is just enough to meet the losses and drive the turbine. So the directional relay for detecting the loss of the prime mover, and it needs to have a high degree of sensitivity compared to the directional relay which is used for overcurrent protection. So for that, what we do, we will have the directional relay with the MTA of 180 degree. We have VA, IA and trip to the generator, and here the MTA in the angle in this case is 180 degree, and when this is the generator, when it is working it is as a generator, and when let us suppose that this occurs, loss of prime mover occurs, then in that very case it is taking IA opposite from the grid, and but the value is very small because of the fact that the real power taken is less. So in this way we can use the this directional relay for that very purpose. So directional relay for the protection against the loss of prime mover. So directional relay. Now let us summarize whatever we have discussed. We will have this. Now for the unbalanced loading. For the unbalanced loading, what we have done, as you know, that for the unbalanced loading, we have connect we detect the what we can say the negative sequence component, and then we can use the extremely inverse relay. As we have seen here, the extremely inverse relay for use for that very purpose. Next is the overspeeding. So tacho generator and the output frequency relay. For the overspeeding, tacho generator mounted on that this generator, or the over frequency relay. Now after that, we have discussed the loss of excitation. So for the loss of excitation, offset mode relay. Loss of excitation, we used a relay which is actually the distance relay, and then we will have this loss of prime mover, and for the loss of prime mover we are using the overcurrent, directional overcurrent relay. So this is about this lecture. We will have the electrical faults and abnormal operating condition. For the electrical faults, we have the three-phase stator windings. Stator faults are there. Phase and the ground faults are catered by the longitudinal differential protection. Interturn faults are catered by the transverse differential protection. Then we will have this short circuit to ground. Short circuit to ground. So this short circuit to ground, it is catered by this scheme that we have discussed. This is the short circuit to ground. So in this case, we have superimposed this overcurrent relay is used, and the voltage is superimposed, and the ground connection is made in that very case. So that is used for this short circuit to ground. Then for electrical stator, three-phase stator winding, we have the unbalanced loading, and we can detect the negative sequence and then use the extremely inverse relay. Then for the rotor field winding or the loss of excitation, we use the offset more relay. For the mechanical abnormal operating conditions, that is overspeeding, we are using the tacho generator and the over frequency relay. And for the loss of prime mover, we are using the directional overcurrent relay. So this is about the protection of the generator. On the next lecture, we will discuss about this protection of the induction motor. Thank you very much.